You are listening to EE Times On Air, and this is the weekly briefing for the week ending September 23rd. This week's podcast is sponsored by Altair, a global leader in electronic system design. As the complexity of printed circuit boards increases, the ability to quickly respond to design changes and achieve higher predictability become the main challenges to meet today's demanding requirements, mainly shorter time to market, lower costs, and of course, improved performance. Modern simulation software is a key solution to those challenges, as it not only allows engineers to predict the performance of a PCB at the earliest stages of design in a short amount of time and with good accuracy, but it also allows us to identify the optimal design among a high number of variations. Joining us today is Jean-Baptiste Moyer, a multiphysics architect with Altair Engineering. He's going to share with us how numerical simulation enables engineers to predict and improve PCB reliability and performance. Jean-Baptiste, thank you so much for joining us.
Thank you very much.
So numerical simulation is such an incredibly powerful tool, and of course it's very much in the news these days, especially with the advances that machine learning and AI bring to the field. It's also an extremely specialized field. Before we talk more about the state of the art on that topic, I'd love to ask you about how you personally got to where you are today. If you're willing, take us all the way back to your childhood. Did you know from an early age that you wanted to go into electronics, or did you have an interest in computers already as a kid?
Actually, as a kid, I had a big interest in computing and engineering. Even from a very small age, I was always interested in thinking about how things, how my environment, how vehicles, how everything in my surrounding world were designed. And then how I could change the design, improved it.
So were you one of those kids who was always taking things apart and putting them back together?
Yeah, I was a fan of Lego.
Of course.
And of some special things which despaired my parents because my experiments were not always very successful. But that's the way we learn anyway.
This is the way we learn.
And so that was the first part. So I would say that I've always wanted to be an engineer. And then things came also in my early teens when this was, I would say, the early 80s, and it was the birth of personal computers. And as a child, I was completely fascinated by those personal computers. And that's where actually my parents offered me one. And that's where I started to develop my own software. And well, of course, at this age, those were mostly games. And I was very familiar with computer.
What was your first computer? Do you remember what kind it was?
My first computer was a Commodore 3032.
Yes, Commodore.
Yeah.
So when you were writing programs in those days, were you writing in BASIC or another language?
I started in BASIC. Actually, it was the only available software. And then I made also a little assembler. Actually, I started my first graphic, I would say, command using assembler to do things that I could not do with BASIC. But that's it. So this is where I started.
And then did you continue that track of study through university? Did you study computer science?
Actually, I was at an aerospace school in which I studied part of computer science, but I also studied a lot of mechanics, structural analysis, or also CFD. And actually, this is where I come to computer simulation, because computer simulation was actually at the intersection between those two fields that I liked, which was science and, on the other hand, computer science. And I could merge them into one single, actually, passion.
Yeah, that makes sense. You never lost your love for physical engineering, and numerical simulation really bridges that gap quite nicely. You've got exactly the right background for it.
Yes, exactly. And that's also why I came later to numerical simulation. Well, actually later, not later, but very quickly. And that was, so I remember that I started simulation to for instance, on aerodynamics, for instance, calculating the flow of fluid around the wing. And more closely I also worked on electronics, but remember that we were in the early 90s and computer power was not as high as now. And so we were very happy when it took only some hours to make very small simulations.
Yeah, that makes a lot of sense to me, thinking about the complexity and cost of making, let's say, a prototype aircraft or even a new shape or design for a wing. Very high cost to actually build that out and test it in a wind tunnel. So it makes a lot of sense that numerical simulation would fill that gap and allow you to test those things. What other experiences did you have in the aerospace industry with simulation?
Actually, when I started working, so it was in 1992, I was in what is called now Airbus, France. And I started my work by doing simulation of vulnerability, as it was called. Vulnerability being to study the behavior and to ensure that a plane will be safe to some aggression. So those aggression may be, for instance, a bird strike, or it may be a hail strike or any kind of impact, a tire burst. And also we consider the crash or ditching. Crash meaning that actually the plane lands landing gear up on the ground, and we must estimate, depending on the situation and the configuration, the damage to the plane. And actually ditching is the same on water. So if you want to have an idea of what it is that you may have to, you may think of the Hudson Miracle, which was also depicted in Huston's movie Sully. Clint Eastwood's movie. And actually, this was something that we were doing. That is to say that we were simulating the full ditching of the plane in the water. And we could estimate, for instance, if there were some leaks of water or some failure, and what were actually the best angle of attack and the best configuration of the plane in order to survive such a dramatic event.
So very low altitude, so very small margin of error, very little time to take any real action, and so many variables. I can't imagine how else you could do it without really powerful simulation technology.
Exactly. That is to say that at this time, we were somewhat, this type of simulation were somewhat at the head of HPC, high power computer, and they were requiring a lot of memory. Actually, the simulation, we did them more deeply when I entered Altair Engineering. So it was in 2000. And this was the occasion to make the first simulation on this topic. And second, this was good because we could trust, actually, we realized that this type of simulations were feasible. And now, actually, nowadays, this type of simulation is often worked on, and there was a lot of progress. And for instance, with the US research organism, which is called in Wichita, in Kansas, is working heavily on this type of approach. We had a lot of progress on this topic, and I was very happy to make one of the first simulation of a full aircraft ditching on water. And to see that this work has progressed and that now we understand better what are the phenomena involved.
That must have been very satisfying to see that play out in the real world.
Yes, somewhat. So honestly, I was not very much involved in the design and involved in the safety of the plane. All the Airbus engineers had already done the job and very well.
Yes, no question about it. So let's shift gears and talk a little bit about PCB manufacturers and the challenges that they face these days and what the consequences are on how they think about design.
Yes, actually, as Altair, we came to PCB design and durability at the request of our customer because they were highly concerned with several problems on this topic. The first one is that they wanted to shorten the process cycle, because if we talk about durability and durability estimate, is the only possible method to do it is still to make some tests. The problem is that an experimental campaign for only one design takes several weeks. And you can imagine that if after the experimental campaign, the design does not meet the specification, for instance, it fails too early, then we have to reconsider the design. And then we have to go to another experimental campaign, and we have to loop until we are satisfied. That is to say that specifications are met. So this is what is difficult. And here, that's where numerical simulation is very interesting, because using numerical simulation, the first thing is that you can have an estimate of how your PCB and how your electronic circuit will meet the requirements and the specification. You know basically that at first, if you meet requirements. And if this is not the case, instead of few weeks to iterate, it takes only few days.
That's huge.
That's huge, yes. And that's the interest, is that you can make an iteration with a few days. When you submit a design to an experimental campaign, you are nearly sure that you will only have one cycle and one experimental campaign, and you're nearly sure that your design will satisfy the design requirement. And that's good, because actually this helps the designers and actually their manager to say, okay, now we know that our product will be ready in a certain amount of time, and we will keep schedules right. It helps to keep schedules. Whereas before, because we had to iterate over a few weeks each time, then the uncertainty on schedules was higher.
Yeah, so not only speeding things up, but also helping to eliminate the uncertainty in the process that can cause even larger delays.
Exactly. And actually, both are interlinked highly. That is to say that by understanding the design, you eliminate most uncertainty first, and second, you speed up design because it's easier to iterate. And also, it's easier to incorporate some design change. For instance, if your customer says, okay, I want to change the performances, and now I want to add for instance, to add more sensors to my ADAS, then you can do it quite quickly, and you can, in collaboration with your customer, you can discuss and come to an acceptable design with the right compromise. But actually, this is the first thing. That is to say, helping and shortening delays is the first part. Mm-hmm. But then we can go to a higher level, is the fact that we can also provide a better design. What I mean by better design is a design which is an optimized compromise between all possible contradictory requirements from design. For instance, basically your PCB, you want it to be as cheap as possible, as easy to manufacture as possible, but you want also to have the highest possible performances. Mm-hmm. And in this case, the interest of numerical simulation is that it will give you the solution that will be the best possible compromise. How can we do this? Well, actually, we start by doing optimization, numerical optimization. So we started to do this on structural analysis, I would say, in the early 90s. And we matured. And now another, science came into play, which is artificial intelligence, and which is greatly here helping on this. That is to say that artificial intelligence and machine learning are helping us to, based on our experience and based on our previous work, they are helping us to find very quickly the right design, which will be the right compromise between all the specifications, such as price, manufacturing difficulties, number of components, performances that you are looking for. Mm-hmm. So, and actually, in this topic, artificial intelligence is a revolution.
I can't imagine how much that has changed how you do what you do in really just the past few years. When I imagine how you were doing this in the 90s, the advances are just staggering.
Yes, absolutely. What is, to give you an idea, before we were only able to make one simulation in few weeks. And once this simulation was done, then we can make some change and rerun. But this was helping because this was shorter than, for instance, developing and constructing and manufacturing an electronic PCB prototype.
Sure.
But anyway, this took some time. Now, in the same amount of time, we are able to make numerous simulations, and not only this, but also to extract through machine learning and to extract all the possible information we could get from all the simulations and deduce, as I said, the best possible design from all those simulations. And this is very interesting because now actually this has a lot of influence on the decision-making process of electronic designer. Because not only you know if your design is satisfying, but you also know how to improve it and what is an even better design. And actually, this was only possible through, I would say, the convergence between simulation and numerical simulation, which means how you will model and how you will calculate the behavior of your PCB. Second is HPC, and HPC means high power computer. With HPC, you can make more simulations, and artificial intelligence that will guide you in the design by first leveraging all the results of your simulations, and second, deducing from all the information that you obtain, improved design. So you see that actually the new capabilities of simulations are possible by leveraging the convergence between numerical simulation, HPC, and artificial intelligence.
So are we at the point already where that process might result in the AI actually suggesting different designs at this point?
Yeah, they are suggesting different designs. By different designs, that is to say that usually, so you are running on a given amount of design, and it will reduce from all those designs. So this is some kind of variant, the design variant, which is optimized. That is to say, it will find, another way to tell it is that it will find the right compromise between existing design, and it will leverage the existing design to create a new design.
Wow.
Though actually it is based on existing experience, which is good because we have the experience and we know the engineer and the decision maker know basically that the existing design is certainly can be a breakthrough, but they know where it is coming from. And this is interesting, people.
Yes, it is. So we've talked about bringing in simulations at the design stage. How early can we bring it in, and what other stages can it be used in?
Actually, it can be used at all stages of the design. Usually, for instance, we can start at early design. So at early design, because the designer does not have, by definition, a full design, usually we are using very small and fine model, which are giving, I would say, some information which are not very accurate and which are basically not representative of the final design, but which are still useful for the designer. So usually the simulations are very fast and very simple. So this is the first level. So here, and then while we are the design improves and the design is being more detailed, in parallel the process is that we are making much more detailed simulation until, for instance, we want to be sure that the design is meeting all specification, especially in terms of durability, on which actually the phenomenon involved in durability, for instance, in the failure process of solders are very complex, and therefore they require very complex model. So when we are close to this experimental compound, and when we want to be sure of the durability of our design, then those models are very complex, and may take few hours to run, whereas at early design, then the model will take few seconds to run. So actually, we can use simulation at all stages of the design. And once again, we only use simulation, but we can also use optimization or artificial intelligence to improve our designs at all stages. And this is also very interesting because not only we can take a decision and we can on the design very early, and you know that design changes are more and more expensive as the design is detailed first. And second, we can also, if when necessary, change the design at all steps of the design phase without endangering the complete design process. We know what we are doing, we know what we are changing, and we know all the consequences of what we are modifying. And this is very interesting. And this is something that numerical simulation allows.
Wow, I had not thought about it in terms of the whole a longer product life cycle.
Yes.
Imagining how much more complex it is. You know, talking about optimizing a design in something with so many components is complex already. But imagining, as you describe, for example, a soldering failure, there must be so many variables. Again, it brings me back to the aviation example. When we imagine a solder failure, we've got factors like ambient temperature, I imagine, and all of the interconnected components, everything that could affect that. Do you look at physical durability as well during those tests? Is that possible?
Yes, I'm saying that actually physical durability is a center problem, and this is what I am working on now. And you are right, this is a very complex and very exciting problem. Because what is exciting is that you must think that you have a large PCB and all its life depends on a teeny ball of metal, of solder. And this is very challenging and very exciting to understand this. And this is why we have to understand how it failed actually. And this is the interest of simulation. That is to say that simulations allows us to predict, for instance, what are the most sensitive solders, where we need to be careful, and where actually we can trust the design, and it's quite easy. This is very exciting to think of it and to see how the simulation results combined with all the techniques I told you of before, HPC and machine learning, will help you to really understand and to somewhat give life to the circuit and to really understand how they fail and then how you can stop this failing.
Yeah. Let's talk a bit more about the process.
Yes.
Imagining a designer, they've got their ECAD. Is that the starting point? Do they submit that to someone like you, and that's where we begin the simulation process?
Yes, this is here. That is to say that we start with the ECAD. And then, based on the CAD, actually, we create the model. To create the model, actually, there are several steps. The first one is meshing. Meshing means that we will model and we will separate the complete structure in a very large number of small elements. And those small and simple elements, finite elements, will allow you to, are somewhat quite easy to calculate. The big difficulty coming, and that's why HPC is very interesting, to the complete sum of all these elements, which can be numbered in millions.
Wow.
And this is how we work, and this is basically the method of finite elements. And so this is the meshing operations. The first thing is to mesh. And then once we have been meshing, the second step is to affect material properties. Once again, knowing the material properties is sometimes very difficult, especially for solders and also for all materials, because the first thing is that they depend a lot on temperature, for instance. And therefore, you must understand how much they depend on temperature, because if you don't take this into account, you will not, for instance, be able to predict the behavior of your PCB circuit at 80 degrees or at minus 40 degrees if you have material properties at, say, 0 degrees. And this is very important. And actually, for this, usually we are calling a database. And one of my job, I would say, one of my function is to populate those material database so that our users can get the right material data depending on the types of solders that they are using. And of course, this is very interesting because if the type of solders they are not satisfied with, they can say, okay, this one is not good. I will take for another type of solder, and I can rerun very quickly the simulation and check if my design is improved or not. And this can be adapted to all materials. So this is the third step. Then a very complex, very deceptively complex problem is that we need to define what we call the loading, meaning what sort of aggression will our model, our numerical model, and in the end our PCB will have to withstand. So for instance, we can talk about thermal cycles starting at initial temperature, then going down to minus 40 degrees for say 1 hour, then going up to plus 80 degrees for 1 hour, etc. So this is a type of loading. We have to model it. Another deceptively important part of the process is to model the load case. So what is the load case? The load case is two things. The first is to define what type of aggression your electronic circuit will be subject to. It can be, for instance, temperature cycling. It can be vibrations. It can be also some small shock. For instance, typically you drop your circuit on the ground. So you can think, for instance, in a classical day-to-day example of a cell phone, you don't want that your cell phone breaks and stop functioning if it falls down on the floor only once. So this is the example. So first level. Second level, and so actually what is difficult, what is very complex is that now I've told you of all those aggressions, and we have to define and we have to what they are exactly. So we can think of a temperature cycle. Usually, for instance, we can say that we will simulate the test, and the test says, okay, people are saying that at the test, the temperature will be between minus 40 degrees and 80 degrees. So say 30 minutes at minus 40, 30 minutes at 80 degrees, and cycling this way until failure. So this is a type of loading. Other loadings, maybe, for instance, when you have for drop test, you will say that a significant drop test will be from this height, say 1 meter. And you will know that when an object falls from a height of 1 meter, you will have, it will fall on the ground at this given speed. All those loadings has to be taken into account. Vibrations, vibration frequency, etc. must be taken into account. So this is what you call the load case. And of course, you have several load cases because first you will know how many temperature cycles your electric circuit is able to withstand. So you will estimate this using numerical simulations. Then what type of vibrations and how long your circuits will stand those vibrations. So this is another simulation, etc., etc. So you have usually a full set of specifications, which is translated into as many load cases. And this is one of the interests of simulation, that is to say, turning natural physical phenomenon into a numerical input that will be very representative of the nature of the physical phenomenon.
What's the next step?
And then the next step is simple, is that once you have done this, you run. So here, this is where HPC is coming into play. That is to say that, for instance, you can submit your numerical models. You can run them on your local HPC, but more and more, the tendency is to submit it on the cloud, so that actually you can optimize your resources and your calculation, because HPCs are expensive, and being able to have some service and submitting your calculation on the cloud means that you only pay when you need them.
That makes a lot of sense.
Yes, exactly.
Yeah.
And yes, and cloud is very interesting for a numerical simulation for these reasons. And so this. Actually, this is some kind of a black box step, which will take few hours, and then you receive the results. And once you receive the results, then you have to analyze them. And usually that's where artificial optimization and data mining and artificial intelligence are coming into play, because all those techniques will allow you to pinpoint what are the performance of the design and why they are performing this way. For instance, if you have an early failure of your electronic circuit due to thermal loading, it will tell you which solder is failing too early, and then you can decide. Or even better, is that the next step is that once you have analyzed, once actually the analysis of your results has been performed, artificial intelligence will suggest you a new design based on the results. And then you can rerun your simulation using a solver. And once you have rerun, you can analyze the results and you can iterate.
Mm-hmm. And improving every step of the way.
Yes,
yeah?
Everything. The other thing that you can do is that you can also estimate the sensitivity of your design. For instance, I was talking about the resistance of your design to temperature. I was thinking about a cycle of 20 minutes at minus 40 degrees, 20 minutes at 80 degrees. But what happens if instead of 21 minutes at minus 40 degrees and say 20 minutes at 85 degrees? What happens? And actually, this will tell if your design is robust or not. And you can also, for instance, take into account sensibility of your design. You may know that you are not, for instance, the thickness of your layers is not always equal to the specified thickness, but you have a certain uncertainties. And it is interesting to know what are the consequences. Basically, this is called the robustness of your design, which means that, okay, if your design is not very robust, it means that it will pass your specification. That's all. But if your design is robust, it means that it will pass slightly above the specification. And this will improve actually the perceived durability of your design by your customers. And it is helpful to know this.
Without a doubt. So you're looking at not only things like the durability of a solder joint, not only the choice of what components you might use, but you might actually be thinking about how those components are laid out and how to optimize the physical location of these things on a board?
Absolutely, yes.
Wow.
This is something that we are working on.
It's absolutely mind-blowing to me how far we've come and how much longer and more difficult this process was just a few years ago. And it's incredibly exciting to imagine where we will be with this in a few years.
Yes, we are expecting actually a big improvement and actually some disruption in the electronic circuit design process.
Yeah.
Using those methods.
There can be no doubt about that. Jean-Baptiste, this has been an absolutely fascinating discussion. It's so exciting to hear about the state of the art today, where we're going. I want to thank you for being here, and I want to invite our listeners to visit the page for this episode on EE Times. We'll have a transcript there, and we'll also have some links to Altair and some other information about numerical simulation. Jean-Baptiste, thank you again so much for joining us.
Thank you very much, Eric. It was a big pleasure to talk about my activities in Altair with you.
That brings another episode of the Weekly Briefing to its end. Thank you for listening, and thanks so much to our guest Jean-Baptiste Mollier from Altair. EE Times released its 22nd edition of the EE Times Silicon 100, which explores the nonlinear relationship between capital investment and technological innovation, and examines the changing dynamics and trends in the global startup ecosystem. This year's edition features startups in areas such as materials, packaging, quantum computing, and security. The book, Silicon 100: Startups to Follow in 2022, can be downloaded to your favorite digital device. Visit the EE Times store at eetimes.com/shop and enter podcast in the coupon code for a 15% discount. The weekly briefing is available through all the major podcast platforms, but if you get to us at our website at eetimes.com, you'll find a transcript along with direct links to the other stories we've mentioned, along with other resources. The weekly briefing is produced by EE Times. It was engineered by Taylor Marvin at Coop Studios. The segment producers were Lady Maya Kane and Katie Huss.